Spatial downsampling is a common operation for efficient object detection. At full resolution, we observe very good accuracy. However, this does not satisfy latency constraints. On the other hand, uniform downsampling has limitations. While it improves efficiency, it reduces accuracy significantly. We propose two-plane prior, a spatial sampling approach that is both accurate and efficient. The key idea of our work is to exploit the inherent geometry of the scene. Uniform downsampling reduces the size of small faraway objects where these detectors perform poorly. Thus, we downsample the images respecting the geometry of the scene, enlarging these objects, improving the detection rate. Two-plane prior shows improvement of 45 to 63% over the state of the art. For more information, please visit our website and come by our poster. Two-plane geometric model forms the core of our method. Consider this scene and the region of interest in the car's translation direction. Corresponding scene geometry is shown on the left, which is our model. Blue plane corresponds to ground plane in the scene. Similarly, orange plane above the ground plane completes the region of interest. This prior, based on scene geometry, is inductive, and both these planes can be mapped onto the scene. We can make two inferences from our two-plane geometric model. First, most of the objects present in the scene lie on the ground plane and within the region of interest. Second, there exists an inverse relationship of object size with depth, namely, height of objects in the image are inversely proportional to their distance from the camera. We would like to warp our image while exploiting these two properties. While we can warp images using perspective warp, there is a limitation. If we wish to process a rectangular image, perspective warp discards image region that may have objects. On the other hand, saliency based warping has two advantages. First, we can focus on what we believe are the important regions, that is, make use of scene priors. Secondly, it preserves all part of the image as much as possible. Thus, we used a saliency based warp and construct saliency map from plane regions defined by our two plane geometric model. Consider the fictional bird's eye view on the left. In the bird's eye view, we define saliency to counter the effect of depth on object size. We map this saliency to the camera view by applying perspective transform using our two-plane geometric model. Based on the two-plane geometric model, we have derived two-plane prior, a learnable layer with very few parameters that can sample scenes while being geometrically constrained. Now we discuss the necessity of the two-plane prior. We observed that solely using ground plane scene prior as saliency distorted large objects like the bus and non-ground plane objects like traffic lights, both depicted in red. Two-plane prior corrects for these kinds of distortions depicted in green. Coming to our key results, two-plane prior is agnostic to the type of detector used and improves any detection algorithm. We observed large improvements in detection of small objects over the state of the art, 45% without latency considerations at the same resolution, 63% with real time considerations. Finally, our approach can be trained without ground truth. We observe better generalization to BDD dataset compared to the state of the art by 36% using pseudo labels. To analyze the impact of two-plane prior at different resolutions, we progressively reduce the size of the image considered. Remember, an image at 0.125 scale is 16 times smaller than an image at 0.5 scale. We observe our detection AP compared to a baseline faster RCNN with uniform downsampling and state-of-the-art approach. As we can observe, we perform better than both at almost all the scales. Interestingly, competing methods fail to detect objects at smaller scales, whereas degradation observed by our approach is gradual and it can detect those objects at that scale. We explore one more key question. Is two-plane prior effective at detecting small objects earlier? From our detections, we associated object tracks using an intersection over union based tracker and observed 10% improvement in average track length over the state of the art. This considers all ground truth tracks. In the figures depicted here, we plotted object tracks of faraway cars X-axis denotes the time they were detected, while y-axis denotes the size of these objects. As we can observe, two-plane prior shows significant improvements and it can detect smaller objects earlier. To summarize our work, using geometric priors to downsample images leads to accurate and efficient detection. Thank you for watching this video. To learn more about our work, please visit our website and drop by our poster at CVPR 2023.